Okay, super. If we were to step inside the Earth and look out.
Can I introduce you?
Yeah, oh, okay, sure. My title slide is next, but yeah, sure, we kind of get all kind of like
We're
meta.
very pleased to have Margarete Jadamec here. She's going to talk about implications of nonlinear rheology for plate tectonics. Thank you, Margaret.
Awesome, great, okay. So if you were to step inside the Earth and look out at the surface of the Earth, with the hypocenters plotted of earthquakes above a given size, a given magnitude, this is what you'd see. And so one of the things you notice is that they're not evenly distributed. And another thing you see is that there's different depth extents. These over here are quite shallow. These ones that we're kind of like running into right now are deeper. Another thing you see is there's a variation in the radii of curvature of these. If one were to do a cubic spline or a surface through these hypocenters, we would see, that those deeper ones have a variation in their depth extent, radius of curvature, and some are relatively isolated. This is South America, and then other ones are, overlapping and intersecting with one another. And so these clusters of earthquakes outline the tectonic plates. And the shallow ones outline either transform boundaries or spreading centers. Transform is where you have shear. Spreading centers is where you have divergent motion. And these deeper ones delineate subduction zones where two plates converge, and due to density differences, the denser plates descend into the Earth's interior. And so obviously, the majority of the Earth is inside the Earth's interior, and thus we can't access it. So we need tools, high-performance computing, other kinds of numerical simulation to simulate the process and understand these observations. Okay, so my name is Margarete Jadamec, and so with that, I'll be speaking about the implications of rheology and geometry on plate tectonics and the role of high-performance computing and solvers in being able to model that process. So plate tectonics, it was in terms of impact, it represented a paradigm shift, a fundamental paradigm shift in earth sciences in the mid to late 1960s. It was a data-driven paradigm, motivated in part by advances in technology and unprecedented mapping of the seafloor, primarily for military purposes after World War II. But nonetheless, the data that resulted from that provided a critical link in terms of solidifying and providing like evidence that indicated that, in fact, there are tectonic plates in motion. This plate tectonic theory provided this first-order explanation for the global distribution of earthquakes, volcanoes, and mountains on the Earth. It provided a self-consistent framework for interpreting these large-scale processes. And so in terms of these processes, in the plate tectonics, the outer layer of the Earth is divided into a series of tectonic plates. There's about 14 or 15 large ones. You could, again, plates like a dinner plate. You could have like a ceramic one or like the Dixie plate or the other ones that like fall in the commercial. So it's a kinematic rheologic construct. It's plate-like in that it has little internal deformation, and the deformation's concentrated at the boundaries. So on average, there's about 14, but again, it's scale dependent. So you could divide the outer surface of the interior, looking at strain rates, into like 52 plates or more. But what we see is there are density variations. The denser oceanic plates descend when converging, interacting with one another at convergent boundaries. The denser ones sink. There's also seafloor created at spreading centers, and you also have shearing. If you're interested in the history, you can look at some of these interviews I had with various scientists that played a role in discovering plate tectonic theory. So we see this motion of the tectonic plates on the surface, and they're descending, but why is that happening? Okay, it's density anomalies, but it turns out that on long timescales, you can actually treat the Earth, the mantle, as a viscous fluid. It's deforming by solid state creeping flow. So you can model it with flow equations. And so one of the things that we observe, one of the things that the evidence and the models converge on is that the interior of the Earth is experiencing, the mantle is experiencing mantle convection, where you have heat, you have a radioactive decay and residual heat from planetary accretion. It's hot in the Earth's interior, and it's cooling outside. We're walking around on this chilled thermal boundary layer. That's not why we're not sinking into the Earth. We're walking on tectonic plates. Inside the Earth, it's hot. It's convecting very, very slowly, centimeters per year kind of thing. But we have this chilled thermal boundary layer of the tectonic plates that we are walking on. And so, so we have this motion of the plates and then convection in the Earth's interior. And so, okay, great. So we get that. And even early on, it was understood the complexity. You can see there's plates here. There's some interacting with one another. And so early on, that was recognized. But again, simulating that process or trying to understand that process in the lab or analytically and now numerically has been quite difficult. And so you can see the complexity of models vary in time. And I just have, like, just for background, the radius of the Earth is a little over 6,000 kilometers, just for reference. Here's the lithosphere. It's about 100 for oceanic plates, about 200 for continental plates. And then the mantle goes down to about 2,900 kilometers down. Okay, so this, so if you want to model subduction like at the surface, the subduction zone, again, where these two plates converge and descend, actually looks quite small now compared to like the whole Earth. But the largest earthquakes occur at subduction zones. Not all plates go down as easily. And so one of the things you might see, I said we're not falling inside the Earth right now because we're supported by these tectonic plates. But of course, over time, in terms of simulating this process, it was not uncommon earlier to actually have like a simulation with no upper plate. Just have a rigid, wood in a fluid and simulate kind of the descent of that material, or have a density-driven, like more viscous layer descend into something less viscous. Because even though we know we have plates and we're walking on them, formulating an interface, so having it such that you can have the two plates, have the interface between the two, have like a rheological equation that can be numerically represented is quite difficult. So it's actually a challenge, and there's lots of approaches how to dynamically represent and have an emergent plate boundary in the models where you have a rheology such that you're rigid in the interiors and you dynamically weaken on the boundaries. It's quite difficult. There's lots of approaches to that. But we know it's important. How those plates interact when they slide is really important, because where that happens generates the largest earthquakes. Like the Tehuka earthquake is one. The Great Alaska Earthquake in 1964 is another one. That Sumatra Andaman earthquake is another one. And so it matters. That process matters for earthquakes and tsunamis. And so I've just got plotted here, super simple, but this is just from, grab this data from the top 500 on the upper right, and and just showing like the size of cores and the RMAX, like running the LIMPAC benchmark, just for, I think this is like 93 to like the mid 2015 or something like that. And it's just showing like the size of increasing computing and performance through time. And so it's this ability that allows us to now take in this geometric complexity and simulate it and examine those processes. And so again, we see that the systems have variation in geometry, curvature, length, width, and depth. Slabs can be isolated or overlapping. This is in the Southwest Pacific. This is the Sumatra Andaman area. And so some slabs can overlap on top of one another. So here in the Western Pacific, beneath Japan, you actually have two subduction zones. You have the Pacific slab going down, and then in southwestern Japan, there's the Ryukyu Nankai slab on top of it. So you actually have two slabs at depth. It's quite complicated. And so, so what's the impact of this geometry? The other thing is subduction zones just don't continue forever around the Earth. They all end. They have lateral terminations in modern systems. So what does it matter if they end? Are there any dynamics that's significant? And then again, what's the role of rheology? Rheology is like modulating the viscosity, modulates your flow rates. What's the role of rheology, and is it important? And again, I showed, okay, we have these access to great compute cores, which I'm super grateful for to be able to do this science. But we know that having enough cores isn't enough to solve a solution, to have enough parameter sweeps done in the lifetime of a research project, of a graduate student, of a graduate research project. Because even though you have access to cores, there's different solvers that are optimal for different kinds of physical problems. And so these are just some simple a bunch of 3D models I ran on maybe something like, something like maybe 30, 48 cores, something of that size, not a lot, less than 64. And what you can see on the vertical axis is the runtime, on this, something on the order of like 32, 48 cores. And so what I did is I looked at, this is in SitComCU, and I looked at the effect of the full multigrid on the solution on runtime. And you could see that depending upon whether you're using V cycle or W cycle, whether your overall viscosity bounds in the model, how you project average the viscosity between levels in the multigrid, those can all, your resolution, those can all have a significant effect on runtime from 0 hours to 15 to some of them not with no solution and not converging. And so so it's in addition to just having the cores, you need to get the algorithms right, or optimize them because it can have a huge impact on the runtime. As you all know, I'm preaching to the choir here. And so so this is a scientific application talk. I'm going to talk about just some results, which are in some codes that use PETSc, some codes that do not use PETSc. And so in terms of scientific applications, why, again, we talked about earthquakes, but I talked about at the same time, it's mantle's convecting and you can solve things with the Stokes equations because it's creeping flow. And so what are a couple takeaways that we can look at? A big question is how coupled are the surface plates to the asthenosphere? So the layer below the tectonic plates is the asthenosphere. It's got a lower viscosity by several orders of magnitude that allows the plates to slide over them. How coupled are they? Are they is there drag the whole way, or are they not coupled in places? What's the real role of rheology in that? And then I mentioned that these slabs have different geometries and that sometimes they have edges. What's the role? Does that matter? Is it significant? Do we need 3D? Do we need all this HPC for the 3D? Do we need all the HPC and the solvers with complicated rheologies? And I talked about these natural systems. I showed that plot with all these complicated slab shapes. Can we even simulate it? And so one of the things I did during grad school was write a piece of software to take in observations and then build three-dimensional input for natural systems on the Earth. And here you just run on the command line, give it different arguments. You pick a mesh input file, so it's a variable mesh. It just got box grid. It ultimately is used in a finite element model, but you just have it's find a week, and you load in different surfaces, your slab surface, ages to constrain the thermal structure, different sort of trim lines if you want to do complicated slab shapes, the endianness of the machine. I know this is really old, and then what kind of output you want, mesh, temperature, input. And so this is an example of a thermal output that comes of the software that I wrote for a natural system in this case, it's at the Alaska subduction zone. This is at the northern end of the Pacific Ring of Fire. And you can see that this is temperature, non-dimensional from 0 to 1, and you can see that the downgoing plate geometry varies. Here it's actually sub-horizontal to flat. This is the location of the second largest earthquake, the Great Alaska Earthquake, the 1964 earthquake. And then as you go to the east, the slab terminates and you have a transform boundary. And so you can take this output from this tech mod, the software I wrote, and then load it into some computational fluid dynamics solver, and then that would have the initial density anomalies that then drive the flow. The slab descends, it stirs the mantle like your hand in a sink, stirring it around, very slowly though, and then because the slabs are plate-like, as they descend, so when the plate gets into the asthenosphere, it's called a slab, when the slab descends, because it's plate-like, it actually pulls the surface part behind it, and that's why the plates move. That's the major driving force. And so we can solve the conservation of mass and momentum and also energy for the viscous flow, where that input, those thermal, that temperature structure comes from TechMod, and that's the driving force. And then the observation suggests that olivine is the dominant constituent in the upper mantle. That has a strain rate dependent viscosity, so we can incorporate that flow law and look at its effects. And so we can start with generalized 2D models and then go on to a couple examples from 3D. So here's our little subduction zone. This is the thermal structure, and this is a viscosity. And we can adjust in these models. Our plate boundary is fixed, and we can toggle how much viscosity variation we have across that interface, and that can modulate how quickly or slowly plates move. And so when we use a composite viscosity structure, that's the Newtonian one, what we'll see in the composite one is you get this dynamic, you get these zones of influence in the asthenosphere around the slab. So what you see, here's our viscosity structure that, whereas we start out just varying viscosity with depth, here's the cold slab, it's stronger. When you have this strain rate dependent viscosity, you non-linearly weaken the asthenosphere around the slab in areas of high strain rate. And what does that mean? What it means is that if you decrease the coupling at the interface, like as a constraint on the model, so this is strong to weak, as expected, your surface motion here goes up. So you make the interface weaker, this speeds up. But one of the things that you don't necessarily expect is that another thing that happens is as this gets weaker, you get more dynamically of weakening in the asthenosphere, and this thickness of weakening below the plates increases. So as our plate interface that we imposed gets weaker, the thickness of this layer gets larger. So when you have this composite viscosity, what happens is the slab descends and it dynamically modulates its viscous support. So if you imagine like a rock, you're dropping it in cold honey, and then you drop it in hot honey, or something that's strong and something that's strain dependent weakened, it would fall. It's the same negative buoyancy, but it would sink faster where you've dropped your viscous support of it. All right, and so when you have this negative buoyancy of this plate sinking, and because of the realistic rheology, you nonlinearly weaken it several orders of magnitude. So what you get then is the surface plates speed up, and the flow in the asthenosphere speeds up. So so one of the things is if you don't have this effect, yes, and you had like a Newtonian viscosity, for example, yes, you decrease coupling here, and the plate speeds up. But when you have this composite effect, you get this like extra speed up of the surface motion, and you dynamically reduce the viscous resistance, thus facilitating the process of plate tectonics. And you can look at this evolve through time. So one of the things we see is that as your slab descends, it sort of sweeps through. As it sweeps through, you get viscosity variations from these strain rates, these variations in strain rates, and then as your slab sort of becomes steeper, you get less of this sweeping. So the zone of weakening varies through time around the slab. And depending upon how coupled you are, if you start with a stronger coupling at the interface, you don't really dynamically weaken enough to have it be sustained. If you start with a weaker interface, over time, that weakening becomes sustained. Because if you think about it, as the plates move, they're shearing below it, because you have a plate moving, not a asthenosphere moving. So as you get more shear, you can sustain it. So that means that this is a way to facilitate the process of plate tectonics by having this composite rheology. And we could not solve these problems without, the composite viscosity, you get these large viscosity variations, large velocity gradients, it's hard for the solvers. So in this code, we have the full multigrid. Other versions of sitcom have used PETSc to facilitate that process. Here's, again, one of the things you find, depending upon we just look at this one. This is surface speed through time. This is time and surface motion. And so the weaker that interface, the more subduction you get through time. If you start out very strong, you don't really sustain that weakening, and you sort of slow, the subduction sort of stops. And so that interface strength can play a role on whether you're going to evolve the subduction zone through time. And so what might affect that? If you have a lot of sediments coming into the subduction zone, if you have a lot of water. So in natural systems, that you can get this variation. And so that has implications for the amount of plates that would be consumed through time. And I mentioned about the 3D. What about the edge effects? We can go back to Alaska, this northern ring of the northern end of the Pacific Ring of Fire, and what is the effect of this slab edge? And this is that 3D input. And one of the things you see in these models, the surface motion, this is a predicted motion in black. This is the subduction zone boundary. And then the white arrow is observed. So in these models, when we're using a composite viscosity, we're able to match the motion on the surface, and it's something on the order of 5 centimeters per year. If we go 100 kilometers down in the asthenosphere where it's weak, we have this edge, and we have toroidal flow around the side. So we have the surface plate going this way on the surface, matching surface motions. But as the slab descends and sweeps, like imagine your hand in the water, you're going to push, assuming an incompressible fluid, you're going to push as the slab steepens, it'll push this mantle this way, around to the side, and you get high pressure and then low pressure. You get this toroidal flow around the side, but then you also get these little upwelling pods because of the 3D dynamics. And these upwellings over on the side, you can see it here. I've got the vertical motion in yellow, so in the lighter colors. So here we have toroidal flow at depth, and then this upwelling. And so that then, we hypothesize, could be an explanation for these volcanoes. Typically, you have volcanoes that sit right above a subduction zone. In Alaska and some other places at these edges, these volcanoes sit off to the side. They can't really be explained in 2D. And so this is this three-dimensional dynamic mechanism to propose for these upwellings off to the side that could be explaining these volcanoes. And this process is facilitated by this nonlinear rheology. Because again, if you're completely coupled, your surface motion and asthenosphere motion should be the same. If the surface motion is going this way and the asthenosphere is going this way, they're decoupled. So that composite viscosity helps to decouple that. And so here's like a view of those upwelling pods. And so in summary for that tectonic process, that rheology and slab geometry place a force order control on these dynamics and can be explaining a new mechanism for these slab edge volcanoes. And that composite viscosity facilitates lithosphere, asthenosphere coupling that allows these upwellings and can facilitate sustained plate tectonics through time. And none of that, understanding these first order processes about how plate tectonics works, we couldn't do it without coupling the solvers with the HPC. And I didn't really talk about effects of the upper plate, but in our models, our trench was fixed through time. You can look at it evolve, and here's some other work with Underworld. I don't think I have time to talk about it, but the Underworld is based on PETSc. Matt's done work on this code. It's Louis Maraisi's code. And then our next steps is to take those three-dimensional systems. This is a Pacific Ring of Fire, and these are different subduction systems. This is output from my TechMod code, to take those and put them into Underworld, and then not only look at the processes I described, but also look at the evolution of the trenches through time, as well as the shorter time scale deformation, like how these background tectonic forces translate to local short-term earthquake cycle behavior. So that is this tectonic application of the scientific application, like intersecting tectonics, earth science, computing, and algorithms. So thank you. And
questions?
Yeah.
So in this model, can you get some kind of a stick slip behavior, or do you have to introduce something?
So the results that I showed for the 3D models, those are visco-plastics. They're looking at this long-term deformation. Matt Nepley is another software that he supports is Pilith, and that does crustal deformation. And so one of the goals is to take some of these models and put them into Pilith as well as Underworld to model that behavior. But if you're going to do a model, even like looking at that, you need the background stresses, like how much would it be subject to? And so these long-term models can provide boundary conditions for that.
Do you remember what roughly the time step on those 2D time dependent ones?
No, not off the top of my head. I have to see in which 2D ones.
The ones that you showed.
From Vivix or from Wendy's? Yeah, I don't remember. Yeah, off the top of my head.
Probably something like 10,000 years, I think, or something like that.
Maybe something like that.
Yeah,
It's going to depend on the coupling. Yeah.
The Maxwell time is about 10,000 years. So stick slip is going to relax before that.
Yeah.
So the process, it sounds like, the descent pulling causes weakening below in the asthenosphere. It seems like that, it sounds like this self-reinforcing thing that accelerates thing and then causes further weakening. So, what is the mechanism that causes that from running away? Is it just kind of the crustal deformation, or? Yeah,
so a couple things. So one of the things, because like in some of the cases, depending upon how weak the boundary was, in some cases you really sort of go faster and then it slows down. In some cases you never reach that. It never really subducts. So one of the things in these models where they're slowing down, they're hitting the transition zone. So the upper mantle, the mantles, it's like the middle compositional layer of the Earth. But rheologically, the mantle is two parts: the upper mantle, the asthenosphere, and the lower mantle. And there's a viscosity jump of about an order of magnitude between the upper and lower mantle at about between like 410 and 660 kilometers depth. So in some of these cases, this like speed, increasing speed, and then that is when it's hitting the transition zone, and slowing down. In some cases, if it just is just weak enough, but not too weak, it just sort of sustains, and then it's like a balance because the velocity gradients from the conservation of momentum have to satisfy the strain rates and the flow law. So there's this extra iteration back and forth. So you have this force balance between the two. So naturally, we looked at this and said, I didn't show these here, but you could say, what if we just let it weaken forever, like put no bound on the lower viscosity of the models? The models don't really weaken below 10 to the 18, and so they only weaken based on like what they're subject to. And so another thing you see is some of them just slow down also because it's a sweeping motion that can like dynamically weaken because you have to make strain rates. So once it can just, if it starts steep, it never really gets weak. But inevitably, they all kind of start with a shallower dip because they're coming from the surface of the Earth. In Wendy's models, she looked at the effect at the transition zone. This is at the bottom of the model box, and these were one with Underworld, and these didn't have that viscosity structure in it. But she looked at variations in upper plate thickness and strength, and found that can also like affect the slab evolution. But one of the things he shows here, it's curling over at that transition zone. Here, it's laying flat. So that's one of the other things that repeat it. Yeah.
So it seems like the plates away from the subduction zones would be really stiff, and so do you have like a coarse grid model of the whole surface of the Earth that you use to build the boundary conditions around your local models, or?
Yeah. As I have this career award modeling subduction along the Pacific Ring of Fire. So I've run these pieces of these areas. I built this one and run them. So as part of this is to stitch these together into one high resolution model. In these regional models, it's high resolution that coarsens outward and then with depth. And so, and they're about 30,000 CPU hours or something per time step. And so for these regional ones. And so the goal is to put these into Underworld or sitcom. Sitcom will have a hard time with it. But to look at that variation, because separately, I don't know if any seismology people here, shear wave splitting observations suggest that there's coupling between the plates in the asthenosphere and the center of oceanic plates, but decoupling at the end. Like the shear wave splitting observations, it's like when seismic waves pass through the Earth, they can split in a fast and slow direction depending upon shearing and fabric, and that you can use to constrain flow. And they suggest you have decoupling of the asthenosphere within some length scale. The dislocation creep deformation mechanism, which is responsible for our nonlinear rheology, and that weakening is the same mechanism that makes the fabric and shear wave splitting. So those length scales should be correlated. And that's one of the things we're looking at in these global models. So we should be able to get that length scale from coupled to non-coupled. And so that's something doing in the global models.
And I think one other thing also is that Margaret has heat flow data off the subduction zones, so that allows you to get estimates of how stiff it is next to it, right? Is that constrains the rheology of your output?
You could use heat flow as a constraint on the output or the input, depending upon what you're testing for.
I guess I have a related
Yeah.
question, a geology question. I was actually surprised to see in your slides, I mean, it was just like in one of your little footnotes or whatever, in one of these, that some of like your rheology is coming from, just lab experiments with olivine.
Yeah.
I would have just figured, I don't know, people just, you kind of fit stuff, you figure out what the velocity has to be to fit, what you're seeing in the field. I was interested to see that some of that comes from the lab stuff, and I was curious, how much does that constrain the material model you're using? And the other question I have, because I took a metrology course like 30 years ago, I know that the upper mantle is mostly olivine, but there's a lot of pyroxenes
Yeah.
in there too. So
Yeah.
you've only got one of the two major components.
Yeah.
How much does that actually matter? What you're doing?
Yeah. Yeah. So let's see. The time scale. This is creeping flow, centimeters per year. When you have this, we know surface motions from GPS, for example. In the asthenosphere, we can use shear wave splitting as a constraint on flow directions, but we don't have velocities. And so but when we use a composite viscosity, these models suggest that you can locally get flow magnitudes in the asthenosphere an order of magnitude faster than plate motions. So like 50, 100 centimeters per year locally, versus surface motions, which are like 5, 10 centimeters per year. So that's about the time. That's like the solid state creeping flow rates for the Earth for this point in the Earth's history, for like our current pressure temperature state. The lab experiments are done like on a much shorter time scale. So there's an extrapolation of strain rates done like over a certain much shorter amount of time to like these. And but one of the things that we do see, there are mantle peridotite that are preserved, that are exposed, and you can look at the fabric, and we do see fabric consistent with dislocation creep in those peridotites. And so that is a constraint that process is happening, and then it also can explain the shear wave splitting. You can get split waves from other things too, but this olivine fabric is one thing that can do it. And so that's consistent. But the rates, it is an extrapolation. And so that's one of the reasons why I didn't show the studies, but we had a variation of like, what if we cap the lower bound in the viscosity to like no bound, to 10 to the 18, 19, 20, and how does that affect the flow rates and this process? And so that's like a second paper we're working on. Yeah, so, but you can also compare these to observations like, regions of dynamic topography like uplift and subsidence and long-term geologic slip rates, and viscosity you can also constrain from post-glacial rebound. And so these numbers seem to make sense, yeah. But one of the different things about this is that this work suggests that you have a lateral variation in the asthenosphere viscosity. So it'd be lower locally than your global average around subduction zones. Did I get most of those? Yeah. Okay. Oh, so olivine. Yeah, we assume olivine. We also have some other models where we looked at fabric and sent shear waves through them, and we can talk more about that. It's an assumption, and so I haven't quantitatively compared that effect. So.
Okay.
Yeah.
I was a geology major.
Yeah. But olivine's the dominant one, but it is an assumption. We also assume incompressibility. We also don't have grain size variations in the upper mantle, which could also affect the viscosity. Yeah.
Well, let's thank Margaret again.
Okay.